Yesterday I forgot to conclude the argument here, for which we do not need actually the specific form of omega. What we know is that this integral will be in a completely covariant form, and what we know is that its variation coincides with the variation of the boundary term attached to S gamma gamma. And that's enough to infer that this new action has all the right properties, because the new action is just the Hilbert action plus this boundary term, so it is fully covariant because the Hilbert action is and this term is, but it is also equal to S gamma gamma plus this difference, and the variational principle of the new action is the same as the variational principle of S gamma gamma, because the variation of this is 0. And the variational principle of gamma gamma is well defined, because gamma gamma, the action gamma gamma is gamma gamma. So there is no problem there. So the variation of the new action is the variation of S gamma gamma, which implies S nu is covariant and has a well-defined variational problem. And then we will see that the variation of why the variation of omega cancels precisely the unwanted terms, which are more or less the analog of this thing, namely objects that in the boundary involve the derivative of the variation. Okay, so to achieve this result, we have to talk about some manifolds, and we were about to define the normal vector to a manifold and show that it exists. So we consider any basis of the tangent to the submanifold in a point, and V0 another vector belonging to the tangent to the manifold, not the submanifold, that is linearly independent of the other three, and then we have a basis for the tangent space to the manifold M in the point P, made of V0, V1, V2, and V3. So we can consider the matrix V mu. So the lower index is this, but each of these is a 4 vector. So this is a matrix, and that is an invertible matrix because these four vectors are linearly independent. Now you can use this matrix to make a change of basis for the metric. So let capital G mu nu denote the matrix V mu V nu, which by this let's say scalar product I just mean the metric contracted with the indices of the two vectors. So it's like a change of basis for the metric g, small g itself. So this is the same metric after a change of basis, so it is invertible because v and g are invertible, and let g denote the inverse of capital G lower indices mu. Then the normal vector can be written explicitly and tilde equal G0 mu V mu, which means that its components are these. Components are those that I obtain placing that index. So this is a normal vector. Yes, so let's write it explicitly. G0 mu V mu. What does it mean? First, it is orthogonal to the vectors that are tangent to the space, tangent to the manifold, submanifold, because it has to be normal to the surface, the submanifold, so this should be 0. And then we show that it is unique, and tilde is unique up to a normalization factor that can be a function, of course, because it depends on the point, but it is essentially unique. So what is this scalar product? This is something like this. Well, it is this. N tilde alpha we can replace with G0 mu V mu alpha. Then we have G alpha beta, V I beta. However, what is this thing? By construction, that thing is G mu I. Capital G with lower indices and capital G with upper indices are inverse of each other, so this is just delta 0 I, so that is 0. So this vector is orthogonal to the other vectors, the vectors Vi, which means that it is has no components on the surface, so it can be only orthogonal. And let n tilde prime denote another normal vector. Then, since V mu is a basis, in the tangent space for the whole manifold, there exist coefficients B mu such that n tilde prime is a linear combination of those vectors of the basis, so we call the coefficients b mu. Then we want n tilde prime to be orthogonal as well to the VIs. N tilde prime VI equals 0, I equal 1, 2, 2, 3. So let's check what this gives. N tilde prime VI, that is n tilde prime alpha G alpha beta V beta I. But n tilde prime is b mu v mu, so that will be b mu v mu alpha, that's component alpha, G alpha beta V beta I. Again, this is capital G mu I, and so we get B mu capital G mu I. Now that is 0. So now we check that n tilde prime and n tilde, which was defined previously, are proportional. Why? Because n tilde prime is b mu v mu from here, and we could write it as b mu g mu nu g nu alpha rho v rho, just inserting a matrix and its inverse. Now we use some information we have, namely that this information here, that b mu g mu I is 0 for every I. So here we have b mu g mu nu. For nu equal to 1, 2, 3, this is 0, and that means that nu can only be 0. And therefore we can write b mu g mu 0 g0 rho v rho. However, g0 rho v rho is precisely n tilde. So you have a normalization factor times n tilde. So the index of the last object is understood. You could write a beta, 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 beta everywhere to make every component explicit. But this is just a number. There is no component here. B mu is just B mu, and G0 mu, G mu 0 is that. The normal vector is unique once it is normalized. Now, here we have three possibilities actually. We'll call it n with no tilde. And we will write n mu, and when we lower the indices by means of the matrix, the metric, we will write it like that. So n squared, by which we mean nn, which is n mu, g mu nu, n nu, or we could also write n mu, n mu. It could be normalized. Once we normalize it, it could be 1, -1, or 0. Because so far we do not know what it is. And so it's unique if it's normalized, if its square is 1 or -1. If it's 0, of course, that's not really unique. So it's unique once it's normalized, if you can, if we can. So in the first case, this is n squared equal 1 is time-like. The second case, it is space-like. And the third case, it is light-like. This is the normal. So we will say that the surface, in the first case, is space-like. In the second case, the surface is time-like. And in the third case, sigma is light-like. Basically, in the third case, n is orthogonal to itself, which is what you may get with Lorentz surfaces, with Lorentz manifolds. But we will not be interested in the third case from now on. We will only be interested in the first two cases to describe the boundary of our manifold. And both cases are actually important, although later we will focus on the first or the second, I don't remember, n squared equal 1, yes. But for the time being, we consider n squared equal to both cases, plus or minus 1. So now we have this vector n, and so we can define a new basis for the tangent. Which is n, v1, v2, v3. So v0 is replaced by n. And we call it w mu. Now, the metric of sigma of the submanifold is h mu nu, which is equal to g mu nu minus or plus n mu n nu. Now we show why this can be considered the metric of sigma. N has lower indices here, and they are lowered by means of the metric of the four manifold, G mu itself. Well, first we observe that when we take this object and raise one index, we obtain a projector. On the tangent space to sigma. To sigma. Well, first we check that it is a projector and then that it does its job of projecting. To be a projector, its square should be equal to itself, first of all. So h mu rho equals what? Well, if we square the delta, we get a delta. Then there is a double product, because n mu has to be multiplied by delta to the left or the right, doesn't matter. So we get twice this. And the third contribution is the square of the last one. But the square loses minus signs, so we get n mu, n nu, n nu, n rho. And this is plus or minus 1. So minus plus 2 plus or minus 1 is minus plus. And therefore you get h. This is, well, this square is equal to itself. We still have to show that it does its job of projecting. So let us check what it gives when you act with h on a vector vi. That should be 0, of course, and that is equal, it should be 0 on the normal, it should be equal to vi itself, but that's also true. Why? Because that is equal to the delta, so vi, minus plus n mu n nu vi mu, but this is the property of the normal, which is orthogonal to vi. So that is equal to vi nu. Instead, if we act on the normal, n mu, we get n nu minus plus n mu, n nu, n mu. And again, this thing is equal to plus or minus 1. So minus plus times plus or minus is minus. And so that is 0. what can we do with that? We can show that this is the metric of sigma more explicitly. That is a 4x4 matrix. So, well, let us consider h tilde mu nu, which is h, this thing that we have written here. So, like that metric, with a change of basis, which is now given by the new basis here. So basically, we contract like that. Okay. If we consider h tilde 0 nu, what do we get? W 0 alpha h alpha beta w nu beta. But what is w0? The definition of w. That's the normal. So that is n h, but h contracted with n gives 0. This is, you can, if you want, raise this index with a metric, the metric G mu nu. But this is 0. And that means that h tilde mu nu is 0, 0, 0, and then there will be something here that with a minus sign is what you can call the metric of the submanifold. Minus sign for the signature. So apart from a change of basis, you see that we get the metric of the submanifold sigma. Now, let sigma be defined by an equation. It's a three-dimensional submanifold, and so it could be defined by one condition on the 4 coordinates, and points that satisfy this condition will be the points of the submanifold sigma. Then the normal is, apart from a proportionality factor, the gradient. Del mu, here we could write partial mu because this is scalar. Why? So let gamma denote a curve on sigma. So gamma will be some x of tau. The tau is a a parameter. When you move along the curve, you are basically, remember what a curve is a map from 0, 1, the interval 0, 1 to your manifold. In this case, it will be the submanifold sigma. Then I can consider, so gamma, the curve, is on the submanifold. That means that this chi function evaluated on x of tau is 0 because the curve stays on the manifold for every tau. Then we can take the derivative of this with respect to tau. That will also be 0. So 0 is the derivative chi with respect to tau, and that is equal to the derivative of x mu of tau with respect to tau times the derivative of chi. So what is the derivative of the curve with respect to tau? That's the tangent to the curve. But the curve can be any curve on sigma, so considering the sets of all curves, the tangent spans the entire tangent space to sigma, and this equation tells you that the gradient is orthogonal to every tangent. So since the normal is unique, this must be the normal up to a normalization factor. So that means that the normal must be some lambda, which can be a function, times the gradient. Now, from now on, we assume n squared equals to 1. Everything will be easily generalizable to the other case. So this will be lambda squared del mu chi del mu chi. That will be equal to 1. So we have defined the metric of the submanifold. Another important notion is the extrinsic curvature. Of the submanifold, which is defined, it's called K mu nu, and that is H mu rho H nu sigma del rho n sigma. So the normal vector is a vector, and the covariant derivative is the covariant derivative. We will assume no torsion, we will assume metric compatibility. So no torsion and metric compatibility. Now we study some properties of this extrinsic curvature, which we will later use to build the boundary term, which is actually a simple expression in terms of the trace of this. But we need to manipulate a little bit to simplify it. We can also write kappa k mu nu equal h mu rho del rho n nu. Why? Indeed, the difference vanishes. The difference is okay, instead of writing the difference, let's write just k mu nu. Indeed, the first definition, k mu nu, can be written as follows, by replacing h, the second h, with its definition, which is delta minus, we have to take n squared equal plus 1 now, so the upper sign, which means minus here, delta minus n. So this is delta nu sigma minus n nu n sigma, partial rho n sigma. And we can drop the second piece and we remain with what we want. Why can we drop the second piece? Because the second piece, you see, contains n sigma del rho n sigma. And that is 1/2 del rho n squared. Why? Because the metric is covariantly constant. There is a metric in n squared, there is not only n and n, but we are assuming metric compatibility, so the metric is covariantly constant, and therefore this is the derivative of 1. Covariant derivative or simple derivative in this case doesn't make any difference, but it is the derivative of 1. Okay, that's first thing. Second thing is to prove that the curvature is symmetric. Which is not so obvious. We study the difference. And the difference is h mu rho h nu sigma. You can write it this way: instead of exchanging mu and nu, we can exchange rho and sigma there. So we collect h mu rho h nu sigma, and we get del rho n sigma minus del sigma n rho. And now we use the formula we found before, that n mu is, apart from a factor, determined by this condition. So this condition up there is the one that, if you want, gives lambda, but we do not need to make it explicit. We just use this. So we get h mu rho, h nu sigma, del rho n sigma, so that's del rho lambda, del sigma chi, and then we will have lambda del rho del sigma chi, minus the thing we obtain by exchanging rho with sigma, so minus del sigma lambda del rho chi minus lambda del sigma del rho chi. So the two covariant derivatives on a scalar chi commute because the torsion is 0. So we have the two simple derivatives plus a Christoffel symbol, but the Christoffel symbol is symmetric. Those two vanish. And the other two disappear. Why? You have h mu rho, h nu sigma. And then we use this again. The gradient, apart from a factor lambda, is n. So we have del rho lambda divided by lambda. Lambda cannot vanish. It has to be by that. So you have del rho lambda divided by lambda n sigma minus del sigma lambda divided by lambda n rho, but that is 0 because h contracted with rho, with n, we saw is 0. And we have two h's. That's why the formula with the two h's is useful, because either of them is contracted with an n in this formula, so that gives 0. So the extrinsic curvature is symmetric. Not only k mu nu is 1/2 the Lie derivative of the metric of sigma. Of h mu nu, which means that it is 1/2. Let's recall what the Lie derivative is. That is the Lie derivative along, we have to specify where to compute it, along the normal n. So that's the same formulas as for the infinitesimal diffeomorphism transformations. If you recall what it is, partial nu n rho plus h nu rho partial mu n rho. We want to show that this is first we show that it can be written, we have already seen it actually, covariant Lie derivative can be written by means of partial derivatives, but also by means of covariant derivatives. when you have no torsion. Why? Because the difference is 0. Because this is equal to what you expect plus terms with the Christoffel symbols. So in the first case you have minus n rho gamma rho mu alpha alpha nu minus n rho gamma rho nu alpha h alpha mu. From the second one you have a plus h mu rho gamma nu rho alpha n alpha, and from the third one you have h nu rho gamma mu alpha rho n alpha. So you see that this one cancels this one, yes, and this one cancels that one. Okay, let's stop 10 minutes and then